Hey Chem students, today we're going to start our next unit, Properties of Matter. This first PowerPoint is pretty basic. You guys have done some of this stuff already, so it should be review. As such, I'm going to move through it relatively fast. I did hand out to you guys the PowerPoint notes. Now, that's different than what I've given you in the past. These ones, if you haven't looked at it yet, because you're like, oh, it's just the PowerPoint notes. Well, these ones actually have blanks in them. So take a look and make sure you fill in the blanks as we go through. Uh, they do match up with the slides uh, pretty much. I think there's, if you notice any things where I'm, off, just let me know. Oh, I didn't mean to skip that. Okay, so one of the outcomes here is describe the properties of gases, liquids, solids, and plasma. So that's something that I'll probably be testing you guys on, hint, hint. And within this as well, we're including these terms, density, compressibility, and diffusion. So those are things you need to know, and some additional key terms that are just needed to describe these things. You already know homogeneous and heterogeneous, hopefully. You know exothermic and endothermic. Hopefully you know the difference between those two. Um, and physical properties and chemical properties is what we're going to talk about as well. Okay, so matter. Anything that has mass and takes up space or volume is matter. So that's basically everything. Like, even air has mass and takes up space. So air is matter. Um, there's very, very little that isn't matter. And what is basically energy. I'm trying to think if there's anything else. Nothing I can think of. So energy doesn't have mass and doesn't take up space technically. So yeah, anything that has mass and takes up space. So everything around you. We've kind of talked about this already, so I'm going to zip through it here. You got your various things underneath matter in different spots. So we've got pure substances and we've got mixtures. Pure substances are particles that make up a substance. They're all the same. So you could have a uh, bucket of gold atoms, or you could have a bucket of salt, and those are both pure substances. Whereas a mixture is a substance that contains more than one kind of particle. So if you had a bucket full of gravel, or I don't even know, uh, a bucket of Lego, those those are mixtures. They contain more than one kind of particle. Um, so here's an example of a pure substance. Even though it's connected together and there's two different colors, they're connected. So that is one type of particle. So that is still a pure substances. For example, that would be like salt, uh, versus this being a mixture. So technically, because you guys know that salt dissociates in water, if you put salt in water, it becomes a mixture at that point, doesn't it? In some way, right? Because you get that dissociation between the molecules, and now you have separate. You have sodium, for example, and um, chlorine. All right, talk about the elements quickly here. Simplest form of matter. An atom is the smallest particle of an element, whereas compounds are forms of matter containing two or more atoms chemically bonded together. Uh, a molecule is the smallest particle of a compound. So you can't go any smaller than a molecule and still be a compound. So NaCl, like one Na, one Cl put together, is a molecule. It's also a compound because it contains two or more atoms that are chemically bonded together. So these are all within pure substances, keep in mind, both elements and compounds. Okay, so again, an example here, something like hydrogen. Actually, no, hydrogen is a bad example because it's diatomic. Something like neon. Neon would hang out by itself. One neon atom here, something like salt, NaCl, and something diatomic. So something like hydrogen is actually a compound because when it's together by its, or when it's together, when it's by itself, it joins up together. I'm so sorry, guys. it pairs up with another hydrogen to make a diatomic as well. Compare that with mixtures where you have two separate particles that are different, two or more separate particles that are different. So heterogeneous mixture, particles are not evenly distributed, often distinguishable. You guys have seen this all before. Heterogeneous mixture, particles of it, I guess, are sorry, that's a typo, evenly distributed and cannot be easily separated. And quickly, the examples there that we've gone over would be something like salt dissolved in water is a heterogeneous mixture because you have salt and you have water that's separate, whereas a homogeneous mixture, that would be salt and water because you can't easily separate that, whereas a heterogeneous mixture would be like sand and water. Those are the obvious ones. Sorry, I'm mixing it up there. It's getting late apparently here. So this table you guys have, there's these different properties of solid, liquid, and gases, and these are fairly important that you guys know the difference between these. This will be something that we'll definitely be testing you guys on. So a solid has a definite shape, whereas a liquid and a gas both take the shape of a container. Volume has solid has a definite volume, and so does liquid. But a gas will take the volume of its container, meaning it will actually expand to fill that container as a gas. Solids are, of course, very dense for the most part, and liquids are less dense than solids usually. There's a couple exceptions. Gases usually much denser than a solid and a liquid, of course. It says usually. I can't think of a situation where a gas is more dense than a solid or a liquid. Yeah, I don't think so. And you have to keep in mind that this is because of energy differences. We'll be getting into it more, but the more energy you add, the further towards gas state you get, right? If you start with an ice cube and you heat it up, it turns into a liquid and then it turns into a gas. And that energy that you're giving it makes those molecules spread out and move further apart. And that's why density is less for the gas. Compressibility. With a solid, usually you can't compress it very well. With a liquid, not easily compressed either. It's why we use liquids for hydraulic systems in like heavy machinery. Those are like to lift up like the loader bucket and stuff like that. Very, very powerful systems with hydraulics. And gases are very easily compressed. We compress them all the time into those like metal cylinders that you see, like your propane tank for your barbecue. That's an example of a compressed gas. And we actually compress it so much that it turns into a liquid inside there. But as soon as you let it out, it turns back into a gas because you've taken the pressure away. We'll be talking about that as well and how that happens later. Diffusion. So not easily, you can't diffuse things across through solids very easily. You can diffuse things through liquids very easily, and you can diffuse things through gases even more easily. And I can think they kind of have to separate them here, but if you put a drop of food coloring on your countertop at home, if you wipe it up soon enough, you're not going to see anything. It's not going to have diffused into that. Diffusing means to slowly move into something. We'll be talking about at the end of this PowerPoint here. Whereas a liquid, you put a drop of food coloring in a cup of water, and you can see how it diffuses quite rapidly to turn that whole cup to whatever color you dropped in there. Can't really use food coloring for gases as an example, but if someone has a bit of gas, let's say flatulence, we're actually quite glad that it diffuses very easily, because if it didn't, you'd have these pockets of fart all over the school, basically, right? Where people have farted and it's like, oh man, I walked through somebody's fart cloud that was there for like the last hour. That would be really disgusting if it didn't diffuse. So happily, things diffuse in gases. Otherwise, things would be very stinky indeed. Okay, the fourth state of matter that we don't really talk about very often is plasma. And this is a gaseous mixture of positive ions and electrons. It's like a superheated gas, basically, a supercharged gas. Um, we're not going to talk about plasma in this very much, and that's because we don't really have plasma on Earth. Not much, anyways. Um, Surprisingly, because 99% of 90% of all matter in the universe is actually plasma. It's kind of bizarre that we barely deal with it on Earth at all when that's most of what's in the universe. And that is because of stars. Stars is the big one. Stars and nebulas, that's plasma up there. And uh, as such, most of the mass in our universe is from stars when you consider, how many stars there are and how huge they are. So 99% of matter in the universe is plasma, but we don't really even deal with that much. We don't have much of it. We have it in lightning bolts. We have it in aurora borealis, which it's not like we can capture that. It's in the atmosphere, well, magnetosphere, actually. Um, yeah, we have these little plasma ball things that you've maybe seen. Um, where you stick your finger on the outside of it and those little uh, sparks, whatever you want to call them, those arcs of electricity will kind of go towards your finger, which is kind of cool. You don't feel anything, but I used to have one and I don't have it anymore. I don't know what happened to it. It's just too bad. I would have liked to have brought it in. All right. Matter has two different kinds of potential properties here. So physical properties that can be observed or tested without changing the composition of the substance, and that is key. So if you're ever wondering, you're like, oh man, is whatever a chemical or a physical property? Spoiler alert, sorry. The other one is chemical properties. Um, you can look and be like, okay, if I test for that, is it going to change the composition of that substance? Okay. So some of those properties would be color. So you can observe or test, well, in this case, observe uh, this property. You can observe color. I can say that this sulfur is yellow, and I didn't change the properties of it. Luster, whether it's shiny or dull, you can see that this is shiny. Malleability, I can bend something, see how bendable it is without changing the composition. It might break it into smaller pieces, like sulfur here. It's not exactly malleable, but it's not going to change its properties. Density, how much stuff is in a certain volume, in a certain space. You can test that by measuring its mass and then just finding out its volume. Phase, its state, whether it's solid, liquid, or gas. Conductivity, whether that's through heat or through electricity. Current, meaning electricity here. You can test that without changing its properties. Solubility, so whether it dissolves in water. That's kind of a tricky one, actually, but this is one that is not a chemical property because you can then evaporate that water and get it back, and it still is that same substance. So you can put salts, right? You can dissolve salt in water or sugar in water, and then you can boil that water off, and you'll still end up with your salt or your sugar at the end. And then viscosity. And viscosity is how easily something flows. Or resistance to flow, I guess, is a better way of putting it, because the higher the viscosity, the harder it is, or the less it wants to flow. So something like syrup has a higher viscosity than water, right? It doesn't want to flow as easily. And as a little sidetrack note here, there's this pitch drop experiment that's been going for almost 100 years now. I don't even know how long. Well, it was started in 1930. Well, it started in 1927, but it only started flowing in 1930. Um, and it's this funnel full of pitch, which is like basically what do they call it? Like bitumen is sticky black. It's kind of like tar, basically, right? Classified as pitch. It's like it's a natural deposit, semi-solid form of petroleum. So yeah, it's kind of like tar, basically. Um, and he put it in there, and then he cut it off, and he put it in this glass dome, and started timing to see how long it would take to actually hit the beaker at the bottom. Uh, here's a there's a battery for scale here, 9-volt battery. And you can see in this picture here, this is in 1990. It started in 1930, so this is 60 years later, and this is just after 2 years after the seventh drop fell, and 10 years before the eighth drop fell. So there's a long amount of time here between. You can see between these drops. This is the years between the drops here. And the last drop fell in 2014. And based on this, next one's going to drop in what, 2028 kind of ish, just a guess. So got some time if you want to go see it, 2028, you guys will be like what, 25, something like that. I don't know. So, road trip, put it in your calendars. All right, back to this. So the opposite of, or the other side of physical properties is chemical properties. And if you want to observe or test these, you're going to change the composition of the substance. So examples of this would be flammability. If you want to see if something's flammable, well, you kind of got to burn it. And you're going to burn it, well, it's going to change its composition. It's going to change its properties. Uh, Oxidizing, whether it is prone to oxidation, whether it will rust or tarnish. Tarnish is like maybe your mom has, or dad has some like actual silverware made with silver, and it kind of turns black over time. That's tarnishing, and that's actually a chemical change. You can clean it off. Uh, Technically, you're losing a bit of silver every time that tarnishing takes place. Rust, obviously, you've maybe had a rusty vehicle or something like that, and you can see how it changes the metal and oxidizes it into rust. You're not getting that metal back. And then reacting with an acid. If something reacts with an acid, it's called reactivity. You're going to not going to get that back. There's no way. It's completely changed the chemical composition of that substance. All right, so those are the three chemical properties: flammability, oxidation, and reactivity, if you want to write down a single word. But you can use those phrases as well. So for example, right here, if we combine H2O and sodium, Na, sodium reacts pretty strongly with water, and it would produce hydrogen gas and sodium hydroxide. If that happens, like if you want to find out, you're not getting this back. This is a complete change at this point. All right, matter. So matter can change its appearance and it will look different, but it could be one of two different types of changes. It could be a physical change or it could be a chemical change. So we have some kind of ways of telling the difference here. So a physical change involves a change in shape or a change in the state of the substance. Okay, so that's fairly easy to follow the rules. So if take your car to the wrecker and he puts it in that car crusher and crushes it into a tiny little cube, uh, you still have a physical change because all the parts of that car are still there. It's just crushed into a smaller space, right? All the little gaps are taken out and it's bent to smithereens. Or if you, let's say, take an ice cube and you melt it with this wonderful animation of flame to a liquid and heat it up even further and it turns into a gas, that's a physical change. It's just changing state. It's still water. Whereas chemical changes, this is when we have a new substance with new properties that are formed. So this is a chemical reaction. And the rule of thumb here is if you're wondering if it's a chemical reaction, can you change it back? Could you go back to the original substance easily? So some of these indicators. So a change in color, a change in smell. That's not how we spell odor. I don't know why that really bothers me. There should be a U in there. So if there's a smell that's produced when something changes, if there's a color that is color change that you have happening, those are indicators of a chemical reaction. Okay, so adding these two colors together, or two colors of liquid together, you would expect something in between that, right? But instead, if you get this dark orange, you can see that that is a chemical reaction. If there's fizzing or bubbling happening, so think of the classic baking soda and vinegar, right? If that fizzing is happening, then obviously that's gonna be a chemical change. So what's happening is it's releasing gas in that chemical reaction. So something like this. Okay, if there's a change in energy, so if the container feels warmer than heat is released, this is called an exothermic change. Exo means outside. So outside heat, therm is heat, outside heat. So putting out heat. Yeah, sorry, I should have just clicked on that, I guess. If the container feels cooler, then heat is actually being absorbed. So this is an endothermic change. So the classic example in this case is you can get those little heat packs where you just like snap them and they get hot, right? And that would be an exothermic reaction, and that's a chemical reaction. You can also get the ice packs that are just room temperature until, again, you snap them and then you get an endothermic change. So, and we have done we did that aluminum and copper sulfates. Yeah, I think that was the one, copper sulfate and aluminum reaction there, where it was like steaming and the container got hot. That was an exothermic reaction, right? Okay, when two clear liquids are formed, or sorry, when two liquids, I can't talk. When two clear liquids are mixed and a solid forms, this is a sign as well of a chemical change. So, or if that mixture goes cloudy, that's called a precipitate, which you guys know about from the last unit. If you get a precipitate, if you get that solution turning cloudy, you've got a chemical change. That is a sign, a clear sign of it. All right, nearing the end here. Diffusion, so how easily one substance is able to move through another. So there must be little interaction between the particles and space for the particles to move. In your notes, so before this took me like a good 5 minutes to, like, I was researching, I was trying to figure out what exactly he was talking about here because there was no comma after particles before. So I read it as must be little interaction between particles and space. Like I was like, there must be very little interaction between the particles and the space in the solution for the particles to move. I was so confused, honestly. And then yeah, I figured it out. I was all of a sudden I read the sentence. I was like, oh, there must be little interaction between the particles of that you're trying to diffuse, and there must be space for the particles to move. Anyways, you had to be there, I guess. It was ridiculous. So what it means here with little interaction, it means that if it's kind of going back to that whole dissociation idea from solutions. If the particles, whatever you're trying to diffuse is more attracted to itself than it is to whatever you're trying to put it in, it's not going to want to spread out. So you don't want that interaction in between there. You don't want that attraction between particles. Now, if they are repulsed from each other, then it'll just shoot out super fast. And then you need space for the particles to move. So space between these other molecules. And that's the reason why it doesn't want to diffuse very easily through a solid because there's less space for those particles to move in a solid. Substances diffuse most easily through gases are the greatest, then liquids, then solids. And that really is because there's more space for it to move between gas molecules, and there's a medium amount for liquids and very, very little for solids. Okay? So that kind of ends us off here. Hopefully you understand these terms and you can describe the properties of gases, liquids, solids, and plasma. We didn't really talk about plasma much, and I'm not going to really test you on plasma much, so don't worry about that one too much. But gases, liquids, solids, that's important, and then make sure you know these terms.